All right, so as we were saying, what were we thinking? An explicable AI train of thought. I oscillate between explicable and explainable. I think the industry or the community is stabilized on explainable AI, or XAI as they now call it, which is the movement within AI research to try and create AI systems whose output is more understandable to human beings and can be challenged and verified post hoc, so that the decision-making processes can be understood. So let's say explainable AI, which is clearly what I said in the email I sent to you. And let's begin. So my thesis in this presentation is that the major trends in AI research that have delivered some of the great gains that we've had in the past 10, 15 years unfortunately lend themselves towards black box style AIs that are opaque to human understanding, and therefore run the risk of making decisions that run counter to the well-being of human beings. Or in more general terms, there's a need to keep the values pursued by an autonomous system aligned with the values of those who create the system. An easy example in this context is if you hire an estate agent to represent you in a sale, their purpose is to act as your proxy, and they should always put your interests in advance of your own. However, an emergent property of real situations is that there is a divergence between the needs of the agent and the needs of the proxy. There's a misalignment, and for example, purely hypothetically, if your agent were also the buyer of your property and did not disclose that to you, then they would not be fully representing your interests in the transaction. So that we call the agent principal problem. And since more and more of our dealings will be represented on our behalf by autonomous systems, intelligent or not, this alignment problem is a global concern pervading all of IT, really, not just artificial intelligence, that will allow us to, or that needs active research. So the key drivers of the kind of modern AI resurgence, because AI, as you may well be aware, has had its ups and downs. It's a very old discipline within computer science, and has gone through various periods of boom and bust, where we tend to make very grandiose promises that we then fail to deliver on, and then funding dries up and we go through a series of AI winters and summers. We're currently enjoying an AI summer, but we might be closer to success in terms where now, if we mess up, we're not just likely to reduce our future grant funding, but we might be in a position now to cause actual harm. So the current big techniques in AI are agent orientation and its extension to multi-agent systems. The majority of the learning systems which you are familiar with and which are having a large impact these days are those built around artificial neural networks. I'm going to make the pitch that, I mean, research hasn't stagnated in other areas, and artificial neural networks can be used to create things that augment human decision making rather than replace it. So we'll take a look at things such as semantic embeddings and latent spaces, and then with an emphasis on human understandable outputs such as decision trees and symbolic regressions and aforementioned semantic embeddings. And this is basically just a position presentation, a rallying cry to not forget those kinds of outputs and push more towards them as an aid to human decision making. So what is an agent? At its simplest, it's simply a way of viewing system development such that you have a very distinct boundary between your system and the environment within which it's embedded. Well-defined points for the agent to perceive the environment through a series of chunks, we call them percepts, and then to take action that modifies the environment in some way through a well-defined interface, which we could call actuators. These could be real-world systems, such as a robot whose sensors would be cameras, and actuators, such as robotic arms, or increasingly software agents whose percept sequence could be a series of messages that they receive, and whose actuators may well also just be a series of messages that they send. The core of the idea of an agent function, in fact, the definition of an agent from a technical point of view, is a system that maps its series of percepts onto action selections according to whatever built-in knowledge of the environment it has, in order to maximize some performance measure. So that's very broad. It covers a lot of intelligent and non-intelligent systems, but as you can probably see, it already biases us towards encapsulating the functionality in a way in which we don't really care too much about how those decisions are being made. It's simply a mapping between percept sequence and action selection, and we are okay with that. So that's the danger of the agent system. Now, obviously, you can't just implement an agent as a magic black box like that. Internally, they will have more sophisticated structures, which I see I did not include that slide. Sorry, but it doesn't matter at the end of the day. The tendency is still towards, however the agent function is implemented, that it is of less importance than the inputs and outputs. So we view them very much as input process output systems. Now, artificial neural networks are the dominant, at the moment, branch of AI which is delivering results. In particular, their application in one particular subset of AI called machine learning, one particular subset of that called supervised learning, where we present a series of examples of states in the environment and the correct action selection that should take place should that state be encountered. If we present our system with a whole bunch of these labeled percept action selection pairs, then over time, if we've got a good performance measure, we can improve the quality of our action selections decisions according to some metric. Now, it's probably worth mentioning that we mostly don't feel like committing to strong words like intelligence per se, although I do see that people are now starting to say things like, for example, ChatGPT has glimmers of general intelligence. The more conservative terminology that's used is that of rationality, which is simply to make the best decision given the limited information that you have. So, for example, if you're crossing the road and you carefully look left and you carefully look right, and you make it halfway across the road before a meteor hits you, the headline the next day in the newspaper won't be "Idiot tries to cross road," because clearly you made the best decision with the information you had. So that more limited goal of rational agency is what we aim for, and in particular, rational agency as an ideal itself isn't even fully realizable, because the search spaces or possibilities that need to be considered can be infinite, or at least untractably large. So we have an even more reduced definition of bounded rationality, where basically, given limited computational memory, storage, information resources, we try and make the best decision we have according to a given utility function or a given measure of performance. So it's very, 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 very qualified. We don't even touch on questions about artificial consciousness and sense of self and so on. So for what it's worth, maybe it's worth stating outright, I'm very much from the narrow, limited AI school of AI, not from the broad general intelligence school of AI. So anyway, the key component in these systems is a very, 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 very simplified version of a cell in animal tissue, which is used for information processing and communication, known as neuron. And when I say very simplified, I mean very simplified. They've done studies, which I probably could have referenced, where they've found that an individual biological neuron is in fact what we consider the equivalent of a deep artificial neural network ourselves. So the individual building blocks in an animal intelligence are as sophisticated as some of our composites, higher level constructs built out of the simplified building blocks that we use. But in any case, a artificial neuron basically takes in a bunch of input signals, which will be converted into some numeric value, multiplies them by weights, which are, again, some real number, combined together. That normally just means that they're summed. It'll often have a bias value added to it just so that we can shift it so that it no longer passes through the origin, and so we can represent a wider variety of functions. And then it will be passed through an activation function, which will do a variety of things. Some of the more common things that they do is to constrain it into a range such as between 0 and 1 or -1 and 1 or so on. But that's not exclusive, and that's certainly not the only thing that they do. But the point is, it's basically a glorified weighted average if you really think about it. The hard part comes to how do we find the correct weights for those things, and that's where learning has to come in. Obviously, one of these building blocks by themselves isn't particularly useful. It can't, for example, distinguish between successfully emulate a simple logical function that we know of as exclusive OR. So not great, but we build them into larger networks by putting them often in layers and then having an input layer that focuses just on the input, multiple hidden layers and output layers. And of course, the structure can be more sophisticated even than that. This now incredibly out of date, but very illustrative diagram shows and it's incredibly out of date, even being only from 2019, shows some of the more common neural network topologies. It does quite notably miss the transformer, which is the neural network architecture that the generative pre-trained transformers, such as ChatGPT and other large language models that I heard you talking about previously, were built on. So you can see that even since 2019, the focus has shifted quite considerably. But the point is that we're in the process of studying a variety of architectures, often for very specific purposes, and some are good for certain tasks and not good for others. The transformers, which you've seen generate amazing results in the last couple of years, are employed in a particular kind of learning known as sequence-to-sequence learning, where the goal is to map a series of inputs and then continue that series of inputs in a meaningful way, according again to some performance measure. Now, the large language models in particular train these transformers on transformer networks on a corpus of data drawn from, let's say, natural language. So their job then is to produce more tokens, more words that feel like the natural language they are trained on. However, it does turn out that they are able to generalize and perform more, a wider range of learning tasks than we expected. So basically, few-shot, one-shot learning, where basically it's the amount of prompting we need to give them to do what we want. But remember, at the end of the day, their job is to produce a series of tokens that feels like a human being wrote it. They have no desire to be correct or to do right or wrong or anything like that. So they are prone to producing completely arbitrary outputs that feel like a human wrote it according to the corpus they were trained on. And we call that hallucination. Although I personally think confabulation would have been a better term, because it's like what human beings do. If human beings are in a strange situation, tired, or had just had a corpus callosectomy or other sort of neurotrauma, and you ask them things that involve portions of the brain that aren't fully awake or fully connected, they will make stuff up. So very famously, the split brain surgery show images to one eye, ask questions of which requires the other side of the brain to the side that I was shown. The person will pick things that correlate to the image that they're being shown, but can't, really notice. And when asked why, they'll say strange things like, "Oh, I just like that image," or "I don't know why I picked it." So confabulation is a thing, but transformer networks do that. They will give you output that feels like the rest of the sequence, even if it's not right or wrong. So the current trend of using them to produce code. It's not necessarily bad in and of itself, because as long as a human being who understands the problem domain interrogates the code, makes sure that it's correct, and then carries on with it, that's could be good. But I just worry that a lot of very dangerous, untested, hallucinatory code is going to be deployed in production, causing a lot of problems. And also the other issue that's emerged is people submitting prompts to ChatGPT for code that contains business secrets and stuff that are covered under non-disclosure agreements. Obviously, the networks run off-site on another company's hardware, so there are definite trade secret issues and intellectual property issues being generated from that practice, let alone the stuff about training large corpus of artistic work for generative adversarial networks, and so on and so on. So there's lots of legal issues that exist. At the end of the day, though, what do these networks learn? They learn a matrix of numbers, which is very difficult for a human to understand. Effectively, this matrix represents a computational graph that just shows the order of operations. You could unpack one of these matrices into such a computational graph, but that wouldn't help you really understand what's going on. It would still be arbitrarily complex. Early thought was that even in the simple multi-layer perceptron networks, was that early layers would learn like low-level features, and higher layers would learn like high-level abstractions, but that turns out not really to be the case. And they can learn some pretty weird things. So, for example, a famous case was a neural network that was trained to diagnose malignant moles. And what it instead learned to do was classify moles that had a ruler in the picture as malignant, because it tended to be the case that if the mole was malignant, then people would measure it and include the ruler in the image. And so it learned the wrong thing. But it took a while to figure that out. Likewise, the famous case of a company that trained its system to shortlist CVs, and what it had learned to do is instead throw out all applications by women, because the historical data upon which it was trained showed that women were less frequently hired and less frequently promoted. So it basically learned to do that. So the embedded bias in the data set became entrenched in the system, obviously hidden in a series of matrices, weights embedded in the matrix, hard to see, hard to explain. If you've got a and it's coming now, it's happening right now, but you'll have people being able to challenge your decisions made by an artificial intelligence and need an explanation as to why they weren't hired, why their loan was denied, why they weren't shortlisted, and you won't be able to provide that other than saying a glorified equivalent of the computer says no, which I don't think will be particularly helpful. Now, I've engaged in research, some of which has been helpful and some of which has been less helpful, making things more complex. So one of the things we've looked at is distributing neural networks over larger numbers of processes, because obviously there's computational constraints we spoke about earlier in terms of bounded rationality. So one particular thing was to implement a convolutional neural network in a distributed manner. Now, unfortunately, that makes it much more complicated. So you get the whole extra layer of emergent interactions between the components that are now distributed, let alone the complexity of the system itself if it were implemented as a single monolithic program. So that made things a little bit worse, I won't lie. Even though the individual components were simpler, the emergent complexity was much higher, as you can see. Now this one, if it's the one I'm thinking of, which it isn't. No, yeah, so this one is also part of that same process of exploring distributed artificial intelligence. This one, however, isn't too bad, not because of the distributed nature, but because of the kind of artificial intelligence system that it makes use of, which is namely a random forest classification, the output of which is something that human beings can understand. I'll show you a slide in a moment in which we take a look at that. And then other kinds of artificial neural network exist that aren't necessarily so focused on mapping inputs to outputs. One which was based on the way in which certain regions of the brain become specialized towards certain tasks is used in a branch of machine learning known as unsupervised learning, whose job is to learn the inherent structure of unlabeled data rather than data where we've got examples of the correct decision. And we've explored using that in combination with particle swarm intelligence to analyze the structure of data. So it's much more understandable in the sense that you can limit the number of nodes that are involved. You don't get an arbitrary output. You just get a sense of the shape of the overall data set. A human being will still need to make judgment calls on that basis, but its just purpose is to simplify. That doesn't mean the actual system itself is simple, as you can see from this very high level activity diagram showing how the system works. But the end result of the system is simply the positioning of these hexagonal nodes in a high dimensional space, and their relative position next to each other gives you a sense of how the data set is shaped. Easy way to think of it is if you think of a very messy table, if you throw a blanket over that table, that blanket will settle and cover the table and capture the shape of the mess that's on the table without the detail. These low dimensional summaries of high dimensional data are very useful, and again, they're for augmenting human decision making rather than replacing it. There are things we can do to make decision making or to make neural networks more visual and maybe more understandable. These self-organizing maps, which I spoke to previously, you can literally view them as a lattice, or you can view them as a sort of image known as a U matrix, which basically shows you the regions in which the greatest differences occur. And also with the transformers, their interesting addition was this notion of something called self-attention, where basically their purpose was to learn sequence-to-sequence mappings, but some tokens in the preceding sequence are more important than others. Let's say words, the ums and ers that you hear from me are less important than the semantically meaningful words, as well as things like prepositions and so on are less important. And obviously context is important, so context will shape what you should focus on. And one of the things that transformers let us do is to learn what we should be paying attention to, and sort of feed that back in a sort of almost strange self loop. But the point is, we can visualize these attention matrices and get a sense of what the network is paying attention to at any particular point in time. That doesn't, however, make the system more understandable. If we're just using it to make a decision or something like that, spit out some output that we blindly trust. So another thing that we can do, and is being actively done, is to map data into positions in a high dimensional space, which we call an embedding. And this can reflect the latent relationships between data points that were unclear in the original training data or corpus. These can result in some very useful outputs in their own right, namely various kinds of embeddings. So word embeddings are probably the easiest to think of, and this example shows that the points in the vector space for capitals and the country they're in will be near each other. Very famously, there's the word-to-vec embedding created by Google, which allows you to do things like take the vector that represents king, subtract the vector that represents male, and the nearest vector that you'll wind up in the vector space is the vector that represents queen, which kind of makes sense because you've taken the maleness out of a king and you're left with a queen. So these arithmetic representations of reasoning in a semantic space can be used as the basis for providing some sort of an explanation as to what you've done. You can basically represent a query that you've made of the system as a point or a path traced through these spaces, and then you can at least provide some sort of information to someone about how you came to a particular decision. Other outputs are inherently much more useful from the beginning. For example, decision trees are a kind of data structure in which we structure things in a tree. Computer scientists like to put trees upside down with the root at the top and the leaves of the tree at the bottom or on the outside. The leaves represent decisions, the interior nodes represent questions that you ask, and the labels on the edges represent the answers that allow you to follow particular paths. Now, decision tree as an output is very understandable to human beings, and a way of generating decision trees or collections of decision trees known as random forest, or other ways of evolving decision trees or creating them, can at least provide you with an output that you can explain to people. Likewise, look, my particular background isn't neural networks. Obviously, I do research in it now because that's where the interest is. But my background is mostly in evolutionary algorithms, which are built around Darwinian evolution. And one of the things you can do with these is you can basically evolve formulas to describe what you want to do. We call that symbolic regression. And there's just an example of some of the research we've done recently that incorporates aspects of epigenetics into evolutionary algorithms. In fact, for what it's worth, this was a PhD student of mine's work, and he graduated last week, so yay for him. And very importantly, for the purpose of understandable AI, explainable AI, is the ability to evolve a formula that you then use as your output. Now, a great family of techniques for that is gene expression programming, which evolves literal string formulas that a person could interpret. A more common but less understandable, but not completely ununderstandable approach is known as genetic programming, which evolves expression trees, effectively computer programs to do the thing for you. I find that a little less explainable because effectively the space of computer programs is infinitely large, and not all of them, you know, will terminate, and some of them it can be a lot more difficult to work with, particularly in terms of how you evolve them, rather than gene expression programming, which combines the ease of evolving simple string representations with the expressiveness of actually creating expression trees for your execution. And it also captures the separation between genotype and phenotype that exists in nature. But one thing they did with this, for example, is they evolved an equation to explain the movement of ions through a semi-permeable membrane in, I think, plants, but I can't remember, but some living cell. And they showed it to experts in the domain who were able to identify sub-expressions that represented well-known formula. It had evolved constants that represented well-known constants for things like, you know, the permeability of certain ions under certain conditions, but they were able to spot those constants in the evolved formula. So at the end of the day, the output of the system was a useful artifact that human beings could use to make further decisions, and not an inscrutable yes-no output or decision output from a neural network that has all of its decision-making embedded in a very inscrutable matrix that's difficult to explain. Rather, a human-readable formula or a tree or something like that that's a bit more easy to understand. All right, I know I've used a lot of time, so I'm not going to actually spend too much time pimping our department, but we exist. We teach computer science. I think we do it all right. We also teach honors. I think we do that very well. Our honors degree in information technology is accredited by the British Computer Society. We also do a lot of short courses. Consider us for your cybersecurity, AI, and IT training needs. Thank you very much.